today a validator consists of three pieces. It is a public-private key pair, it is a machine, and it is an agent. An agent we look at as an individual or an entity. So it's three things. And all of those are super monolithic. And that's just the validator stack of today from an Ethereum perspective. What DVT enables is a more modular validator stack. And now what happens post DVT is you have key shares, not just one public-private key pair. You have a collection of key shares, as many as you'd like to create based on your trust, properties, essentially. The next piece is that those key shares then can go on multiple machines, not just one machine, but multiple machines. And then third and lastly, this validator can be run by a group of people or a group of entities. So it takes your modular validator today, super monolithic, and it takes it to the more modular version where you can have multiple key shares. It increases your security. You can have multiple machines. It increases your availability, and you can have multiple people or entities. Therefore, it increases kind of your game theory or decreases the chances of Byzantine behavior for that validator. And I'll give it to Oisin, and he can go more into kind of the technical talk.
Yeah, I think one of the interesting things about it, or what makes these distributed validators more possible than they might otherwise be, is the cryptography that Ethereum 2, we should probably stop saying the word ETH2 uses, proof of stake Ethereum, and that's the BLS signature scheme. What's fancy about the BLS signature scheme is it's one of the first elliptic curve signature schemes where if you have independent signatures all for the same hash, you can actually add them together in a low trust environment. You don't need the original private key to do so. So what happens, as Collin alluded to, is you want to set up a distributed validator. The first thing you probably do is a distributed key generation, unless you want to just split a normal key locally. But it's better if you kind of do one with a DKG. Then at the end of that process, there's let's call it 4 machines to keep it easy, each with a piece of the private key on it. And you have a piece of software in the middle of your validator stack between your consensus client and your validator client. And these 4 nodes can connect to one another over TCP, and they more or less play a little consensus game to decide on what they're going to sign every time that there's a validator duty coming up. They play a little consensus game, pick this is the hash we're going to sign, and then every validator client is given the exact same hash to sign. They all, check it for slashing rules, do all the usual things. What's nice is everyone gets to keep their own private key management. The Obol software is just kind of read-only as a middleware. It doesn't actually have the power to sign anything. So all of the independent validators check that nothing's flashable. Once they're happy, they sign it with their piece of the private key and they broadcast it to what it looks like their consensus client. And then in the middle there, our software intercepts them, shares them around with the other machines. And once any of, in this instance, a 4-node cluster, once 3 of them, 3 of the signatures are together, you can combine them into a full valid signature for the validator, and you can send that onwards to the network. And what's neat about that is you don't need all 4 signatures. You actually can have fault tolerance. And this is kind of one of the super important things about high availability is if you put, a validator on 4 machines, but you need all 4 of them to be online, you're more brittle than you would otherwise be. But if you put it on 4 machines and only need 3 to be online, this is where things really start to change. And you can have high uptime, you can do rolling restarts, you can replace hardware that fails without downtime, and all of those good things and are kind of unlocked with distributed validators.